Hello everyone, I will present our paper Comparative Analysis of AR, VR, and Desktop Tools for Prototyping Augmented Reality Services. To recall some context, situated authoring refers to the creation of AR experience in a dedicated space. It can mean adapting an AR service to a home, creating an AR experience in a museum, or even an AR maintenance procedure in a factory. Today, creating such content is still a difficult task, in particular for users without 3D and development skills, as it requires the use of advanced tools and programming languages. There are three categories of tools for AR situated authoring. First, desktop editors leverage 2D interactions to let authors associate AR content and behaviors to the real world. Second, VR editors propose to immerse the users in a digital twin of the target environment to prototype AR content. Last, AR editors enable authors to edit their content directly in the real world. In the context of training scenarios authoring, Gonzalez et al. Highlighted similar performance and usability between an AR and a desktop editor and increased physical load and feeling of efficiency with AR. This paper then presents a complementary study to this one with a focus on spatial authoring and not on creating advanced behaviors in order to target only users without 3D development skills. We include a comparison with a VR editor that provides the exact same capabilities as the AR tool and that relies on the same device setup. We also aim to explore the impact of the environment size, and it can also induce differences between the interest of each tool. Our goal is to highlight insights and possibly guidelines for developers of such authoring tools. Our approach then relies on a comparison of the three different types of tools, desktop, VR, and AR, for different criteria such as performances, usability, and cognitive load. The three tools have been designed based on existing solutions such as Unity or ShapesXR, allowing us to link the study results with existing tools. All the tools have the same capabilities: navigating in the environment, adding, moving, and deleting content. In particular, the AR and VR editors use the same ray-based interaction technique for selection and manipulation. Both immersive editors relied on the same MetaQuest 3, and we used the video pass-through mode for AR. These three editors were compared in a user study with a between sub-X design. Each user only tested one editor to avoid any learning effect. We collected inputs from 42 users separated in three equivalent groups, all office workers and all considered as novice in the field of XR, no developer, no experience with 3D tools, and not owning a XR device. We asked them to create two AR services in two environments, a small and large one. Users were asked to add a specified number of selected AR assets to the scene and place them in the real environment to optimize the user experience for the end user. We used two different scenarios that are classical in the field of AR. First, we addressed a smart home scenario where users were asked to spatially position AR assets in a living room, specifically for controlling its connected objects with dedicated interfaces. Second, in a larger space, we addressed a security patrol guidance scenario where users were asked to place guidance assets and interfaces for interacting with the connected objects of the building. We applied a counterbalancing design to ensure that half of the users in each group started with the first scenario, while the other half began with the second. Users started with a training session of approximately 10 minutes, and we also collected SSQ data at the beginning and the end of the experiment. We collected both subjective and objective data, in particular task duration, cognitive load, through NASA TLX, usability questionnaires. Our first hypothesis aligns with the findings from Gonzalez et al. We were expecting few difference between the three conditions for the smart home scenario. However, we were expecting differences due to the larger size of the environment in the second scenario. We thought that users would be faster with the VR and desktop tools, as these do not require physical navigation. We also thought that user experience and preferences would be better with the AR editor, as they would enjoy navigating in the real environment and would find it more aligned with the task. We first looked at performances differences between the editors. These results must be analyzed carefully, as we did not instruct users to complete the task as quickly as possible. For the positioning of objects, some users were more careful than others, and all did not adopt the same strategy. For instance, some users placed the interfaces close to the corresponding connected objects, while others placed them all at the same place to create a dashboard. What we observed is that users were faster with the immersive editors compared to the desktop one in both scenarios. What is interesting is that with the large environment, the difference was only significant between the AR and the desktop editors, which does not indicate the expected advantage of VR in that context. The number of manipulations was similar across all editors. We also observed differences in positioning, particularly by examining the distance between each positioned interface and its corresponding connected object. These differences were not significant and were mostly due to perspective issues, as we noticed some assets placed completely outside the environment with the desktop editor. Regarding the NASA TLX, we only observed significant differences between the AR and desktop editors. In particular, for both scenarios, the temporal demand was higher and the perceived performance was lower with the desktop tool. For the security patrol scenario, frustration was also higher for this tool. Contrary to our expectations, we did not observe any significant difference regarding physical demand. Overall, the results regarding user experience follow a similar trend. The SUS questionnaire indicated better results for the VR and AR editors. Specifically, for the first scenario, a significant difference was observed only between AR and desktop. In the second scenario, significant differences were noted between AR and desktop, as well as between VR and desktop. Custom questionnaires globally highlight the same observation with better usability and feeling of success with the AR and VR editors. Regarding differences between the two scenarios, we only observed an increased feeling of creating an AR service for VR and AR tools for the first one, and better comfort for the same editors in the second scenario. Only one significant difference was observed between AR and VR. The VR editor was considered less frustrating with the second scenario, but this observation was not confirmed with the NASA TLX. Globally, our first hypothesis was not validated as we observed better performances, usability, and workload for both AR and VR editors in comparison to the desktop one. They do not align with the previous study from Gonzalez et al. The observed differences may be attributed to variations of devices, tasks, and interactions, and also to our panel of novice users. Similar differences were observed with the second scenario, which tends to confirm our second hypothesis. However, users were faster in AR, while we expected advantages for VR and desktop, as they did not involve any physical navigation. The results only partially support the second part of the hypothesis, as only major differences between the AR and desktop editors and between the VR and desktop editors were observed. For the second scenario, the frustration criterion appeared to be more significant with the VR and desktop editors, suggesting a potential difference between the two tools that could be attributed to virtual navigation or the feeling of being isolated from the real world. So here's what we can conclude about the paper. Overall, the results highlight a greater interest in the immersive editors for the different evaluated criteria with more significant difference in favor of the AR setup, suggesting that this tool stands out somewhat. Contrary to our expectations, the impact of the scenario and environment size on the results were minimal, with a consistent trend favoring the AR and VR editors. From the user feedback, potential guidelines suggest that tool creators should prioritize immersive editors for novice users, incorporating natural interaction techniques as well as an immediate testing mode. We think that desktop editors just need to be adapted to better correspond to the skills of novice users, for instance by taking inspiration from video games. We see an opportunity to develop an all-in-one tool that offers, at the right time, desktop, AR, or VR experience, thanks to the new generation of mixed reality headsets. If we want to extract more robust guidelines, some questions still need to be addressed. First, the question of environment size requires deeper exploration. The difference in size between our two environments may not have been sufficient to observe differences. It would be interesting to test in larger environments, for example, in an entire building or in a part of a city. Second, the learning effect could also be investigated in a long-term study to evaluate whether different results are observed over time. In particular, how VR and AR are appreciated beyond the novelty effect. Third, more results are needed to assess the impact of these editors on accurate object placement and the development of more advanced behaviors as we focused on a simple positioning task. To finish, the advancements in generative AI could provide a lot of opportunities for such editors to simplify the creation process, especially for novice users, by enabling the generation of assets, scenes, and behaviors. Thank you for your attention.